Hi everyone. In this video, we're going to review exam number 2 on kinematics. In the first lesson, we learned the difference between a scalar and a vector. A scalar is a quantity that has magnitude only. For example, temperature is a scalar, 32 degrees Fahrenheit. Vectors have magnitude and direction. For example, wind speed. When we say the wind is 30 miles per hour out of the east, that would be a vector. The ones we really concerned ourselves in the beginning of the chapter with were distance and displacement. Distance is a scalar and is the length of the path followed, whereas displacement is a vector and it's the straight line distance from the starting point to the ending point. So if someone walked from point A to point B and did so along this path, the distance they traveled would be the length of the line. Whereas their displacement would be a vector from their starting point to the ending point. The first question we saw about this on the test was number 10. A student on her way home from school walks 4 blocks east, 3 blocks north, and another 4 blocks east, as the diagram shows. Compared to the distance she walks, the magnitude of her displacement from home to school is. So the distance, shown in red, would be the length of all this. 4 plus 3 plus 4 would be 11 blocks. But her displacement would be the straight line distance from her starting point to her ending point, and a straight line between any 2 points is always the shortest path, so we can see that the displacement is less than the distance. In lesson 2.2, we learned how to add vectors graphically. This meant we drew scaled diagrams, where a certain number of centimeters might mean a certain number of meters or kilometers in real life. And we would put those vectors tail to head. So first we walked, let's say, 30 meters to the east. We might draw a 3 centimeter line to the east using a scale of 1 centimeter equals 10 meters. If then we walked north 40 meters, we would start that second vector with its tail on the head of the first vector. We'd make sure it's 4 centimeters long, because that would mean 40 meters. And then the resultant, the total displacement from the starting point to the ending point, would be drawn like this. And we can use a protractor to measure this angle. And we can use the ruler to measure the length of this side. In this case, it would have come out to be 5 centimeters. And we would have converted that into meters, and it would have been 50 meters. So my displacement here would be 50 meters and this angle, if we measured it, would be 53 degrees. And we'd have to say where we measured the angle from, so like north of east. Now there was a question that used this on the test, but it included some other stuff, so we'll come back to that in a little bit. After learning how to add vectors graphically, we learned how to add them algebraically. And this required a long process, but some of the key points that we had to learn were that vectors have components. So if this vector is 100 meters and it's drawn at an angle of 53 degrees, then the x component is how far it points horizontally, and the y component is how far it points vertically. To figure out this x component, which is adjacent to the angle, we would use SOHCAHTOA. And since we always have the hypotenuse in these type of problems, and x is adjacent to the angle, I would use cosine. So cosine of 53 equals adjacent over hypotenuse. Really, I should write everything in terms of variables, so let me make this a theta for now. On the next line, cosine 53 degrees equals x over 100 meters. And if you put this in your calculator properly, you would end up with 60 meters for x. Now, if you wanted to find the y component, which is opposite the angle, you would just use the sine function. Then what we'd do is we'd add up all the x and y components of all the vectors we wanted to add, and we'd make a new right triangle, and we'd try and figure out the hypotenuse using the Pythagorean theorem, and the angle using inverse tangent. We saw this applied on questions 13 and 14 on the test, and you'll see 15 we'll come back to in a little bit because that'll be something we did a little bit later. But question 13, determine the measure of the angle in degrees between the resultant and the 1.4 kilometer displacement vector. I'll remind you we crossed off part of the question here and we said this was not to scale, and so that forced you to do this algebraically. Well, when I look at these two vectors, I can see they're perpendicular to each other, and the resultant would be something like this, and it forms a right triangle. So for number 13, if I want to figure out this angle in here, if I have opposite and adjacent, I would use tangent. Very important that on part 2 questions you write your equation first, then your substitution with units, and then your answer. Now some people have trouble typing this into the calculator. I would type 0.7 divided by 1.4, which gives me 0.5, and you have to take the inverse tangent, which on most calculators there's a second button, and then the tangent button, and I get about 27 degrees. Next, they want me to determine the magnitude of the girl's displacement. So that's the distance from point P directly to the endpoint, the length of this vector. Since it's a right triangle, I could do the Pythagorean theorem. I would write a squared plus b squared equals c squared. 1.4 kilometers plus 0.7 kilometers equals c squared. Putting that in my calculator, 1.4 squared plus 0.7 squared. I get 2.45, but don't forget to take the square root of that, and I get 1.6 kilometers, or 1.56 if you had one more significant figure. Question 15 is about speed, so we'll come right back to that. The next set of quantities we learned about were speed and velocity. Speed is the scalar, and the formula for speed, so the bar above the v means average, and we use v for speed, is distance over time. The vector version of speed is called velocity. And we use the same formula, but if we want to find velocity, we don't do distance over time, we do displacement over time. So I actually want to go back to our last part 2 question, number 15. So in question number 15, it says calculate the girl's average speed. And they're trying to get you to, they're testing whether you know the difference between speed and velocity. And you have to remember, to find the speed, we're going to use the formula v equals d over t, where v average is the average speed. And if you're trying to find speed, you have to put distance over time. And distance is not the 1.56 that we got in the last problem, but it's the length of the path followed. So the 1.4 kilometers plus the 0.7 kilometers. So we went 2.1 kilometers in 12 minutes. 2.1 divided by 12, I got 0.175, so I'll put 0.18 kilometers per minute. Now some people took the time to convert the minutes to seconds and maybe the kilometers to meter, and that's fine to do. It didn't tell you what units you had to put it in, but these are the simplest. In number 5, a car travels from the 100 to the 250 meter highway markers in 10 seconds. So if they went from 100 to 250, the distance they traveled was 150 meters in a time of 10 seconds, and we want to find the average speed. So I use v equals d over t, 150 meters over 10 seconds. and you get 15 meters per second. Choice B. For number 6, a blinking light of constant period is situated on a lab cart, which represents a photograph of the light as the car moves at constant velocity. So this is like our spark timer labs. If something was moving at constant velocity, we'd get equally spaced dots throughout the paper, like choice C. Question number 9. The speedometer in a car does not measure the car's velocity because velocity is a vector quantity and has a direction associated with it. And so our speedometer is only giving us the speed, not the direction. Choice A. In this lesson, we did questions that involved relative velocity, like a riverboat question. Here we have a boat that's trying to make its way across a 75-meter wide stream, and its velocity in that direction is 3 meters per second. So 16 says calculate the time required to cross the river. So I would do V equals D over T. Seventy-five meters is the distance. We're looking for the time, and the speed is 3 meters per second. So when I manipulate this, I bring the t to this side and the 3 under the 75, and so 3 divided by 75 gives me 25 seconds. Now we go back to that graphical vector addition that we talked about in lesson 2.2. On the diagram, use a ruler and a protractor to construct a vector representing the velocity of the river current. Now the velocity of the river current is 2 meters per second due east. And they ask us to start at point P and use a scale of 1 centimeter is half a meter per second. So if we want to have 2 meters per second using the scale that 1 centimeter is going to be 0.5 meters per second, we need to make this 4 centimeters long. So starting at point P, construct a vector to the right that's 4 centimeters long. In number 18, we want to figure out what the resultant velocity of this is. And it says to show your work if you're going to do it algebraically, so you'd have to show the Pythagorean theorem. And if you did that, it would look something like this. You would write a squared plus b squared equals c squared. 2 meters per second squared plus 3 meters per second squared equals c squared. Putting that in the calculator. 2 squared plus 3 squared gives me 13, and then I take the square root of that, I get 3.6. meters per second. Now if I wanted to do that graphically, I can't have it the way it's drawn in this picture because those vectors are not tail to head, so I have to move one of the vectors. I'll move the 4 centimeter arrow this way. And then what I'm trying to get is the vector that goes like this. If you measured that, that would be 7.2 centimeters, and 7.2 centimeters would be equivalent to 3.6 meters per second. And that's what you have to write on the answer line, 3.6 meters per second. In lesson 2.5, we learned what acceleration was, which is any change in velocity. So an object that speeds up or slows down or changes direction is accelerating. And the formula that goes along with this is that acceleration is the change in velocity over the time. Now, in the next lesson, I explained that we can convert this equation into, if I make Vf minus Vi for change in velocity and I rearrange it, I get Vf equals Vi plus At, and I prefer you use this equation whenever possible. And so I don't think there are any questions where you had to use this first equation here. In lesson 2.6, we learned, or we actually derived 3 equations. Vf equals Vi plus At. Vf squared equals Vi squared plus 2AD, and D equals VIT plus 1/2 AT squared. So now we're starting to develop a lot of equations. We have our V average formula. We have actually a second formula for V average, which is just the definition of averaging. Add up the two numbers, VF and VI, and divide by 2. And then we had that formula A equals delta V over T, which I said we're probably not going to use because it's very similar to this equation. But we have really these 5 equations we might be choosing from, and so it's very important that we use the guess method. I'll remind you that the guess method means that you should write down your given information and what's unknown, the thing you're trying to find. And then you're going to write the equation that has the given and the unknown in it with nothing else. Then you're going to substitute in your numbers with units and get the solution with units. And if you follow this guess method, you're much more likely to get the problems right. So let's try that guess method on number 7. A car initially traveling at a speed of 16 meters per second, so V initial is 16 meters per second, accelerates uniformly to a speed of 20 meters per second. So at the end of the problem, the final velocity is 20 meters per second. Over a distance of 36 meters, what is its acceleration? So I have my given and my unknown. The equation that has these 4 quantities and nothing else is VF squared equals VI squared plus 2AD. So 20 meters per second squared equals 16 meters per second squared plus 2A, 36 meters. So on my calculator, 20 squared minus 16 squared, that's going to equal 144 divided by 2, and then divided by 36, and I get an acceleration of 2 meters per second squared, choice B. Change colors for number 8. A roller coaster traveling with an initial speed of 15 meters per second decelerates at -7 meters per second squared to a full stop. So that's a cue that V final is 0 meters per second. How far does it travel? So actually it turns out that this is going to require us to use the same equation. VF squared equals VI squared plus 2AD. VF is going to be 0. VI is 15 plus 2 times -7 D. So the first thing I'll do is 15 squared, and I get 225. When I subtract it onto the other side, I get -225, and I have to divide that by 2, and I have to divide that by -7. And when I do that, I get just about 16 meters. For number 11, a rocket initially at rest, so V initial equals 0, lifts off vertically at a constant acceleration of 2.0 times 10 to the 1 meters per second squared. How long will it take, so I'm trying to find time, for it to reach an altitude, which is like a distance, of 9.0 times 10 to the 3 meters? So with this given information, the correct formula is D equals VIT plus 1/2 AT squared. Since VI is 0, 0 times T is going to be 0. I can cross that off right away because it's going to be 0. 9 times 10 to the 3 is 9,000. You can just write that out, or you can leave it 9 times 10 to the 3. 2 times 10 to the 1 is 20. And I'm looking for time. So I'm going to do 9,000. To get rid of the 1/2 on the right side, I'll multiply the 9,000 by 2. And then I'll divide by 20. And then I have t squared left, so I have to take the square root, and I get t is equal to 30. Now 30 seconds is the same as 3 times 10 to the 1 seconds. In our last lesson in this chapter, we learned about graphs of motion. And we learned how if we have a distance time graph, the slope of that graph is equal to the velocity. And when we have a velocity time graph, the slope of that graph is equal to acceleration. And if we wanted to figure out something about the distance or the displacement, we would find the area under the graph. So in question number 1, on a displacement time graph, I asked during which time interval is the object accelerating. Remember that the slope of the distance time graph tells me about velocity, and if I'm accelerating, the velocity is changing. So I'm looking for a part of a graph where the slope is changing. That occurs from 3 to 4, choice C. In 2, I ask, what is the average velocity from 0 to 3 seconds? Now, velocity on a distance time graph is slope, but I have a broken line here. It has a line that goes up like this and then a flat line. And so I can't find the slope of those two different lines. What I could do is I can insert a straight line and do change in y over change in x. The change in y, it went from 0 to 3 meters. So 3 meters minus 0 meters over, and that was 3 seconds and 0 seconds, and you get 1 meter per second. Another way to do it is just use the equation v equals d over t, and it went from 0 to 3 meters, so the distance was 3 meters in 3 seconds, and you get 1 meter per second. Choice A. Now in questions 3 and 4, it was a velocity time graph, so don't forget, on a velocity time graph, the slope is going to give you acceleration, the area is going to give you distance. This paragraph above tells us that any positive velocity means it's traveling northward. Or actually it says it's initially traveling northward, and so those are initially positive numbers. So what happened with this train is it sped up northward to 20 meters per second in the first 3 seconds. And then between 3 and 5 seconds, it started slowing down until it stopped at 5 seconds and reversed directions. And now it has negative velocity from 5 to 11. So it says in what direction is the cart traveling at 4 seconds? At 4 seconds, the velocity is still positive, so it must be traveling north. Question 4 asks, what's the acceleration at 8 seconds? At 8 seconds, you can see we have a flat line here. The slope is 0. It's not changing velocity, and so the acceleration is 0. For number 19, we have a speed time graph, which is like a velocity time graph. And so if we want to figure out the distance, we're going to take the area under the graph. This wants the distance for the first 3 seconds. So the area I'm concerned with is the area of this triangle. The area of a triangle is 1/2 base times height, which is 1/2 3 seconds times 4 meters per second. When I type that in the calculator, I get 6 meters. Now, many people are going to try to do v equals d over t for this problem. But don't forget what that v bar means. That line above the v means average. And so I can't plug in 4 meters per second as my average speed. My speed went from 0 up to 4. My average would have been 2. And if you did that, 2 meters per second was my average speed for those 3 seconds, then you would have gotten a distance of 6 meters, and that would be good. Okay, the last question on graphs included some other things as well, 20, 21, and 22. A car on a straight road starts from rest and accelerates at 1 meter per second for 10 seconds. So let me write this given information. Starts from rest, accelerates at 1 meter per second squared for 10 seconds. After that, it does another kind of motion. It continues at constant speed for an additional 20 seconds. Determine the speed at the end of the first 10 seconds. So I want to find the final speed for this bit of given information. And so I'll use the formula Vf equals Vi plus At. Vf equals Vi was 0, A was 1 meter per second squared, and the time was 10 seconds. And so Vf is 10 meters per second. That's the answer to question 20. On 21, it says, on the grid provided, use a ruler or a straight edge to construct a graph of the car's speed as a function of time for the 30 seconds. So we just figured out that for the first 10 seconds, it goes from rest up to a speed of 10. Now it does that with a straight line because it's accelerating at 1 meter per second squared. So the slope of that line everywhere must be 1 meter per second squared. After the first 10 seconds, it travels for 20 seconds at constant speed, and so you keep it at 10 meters per second until you get to the 30-second point. Now in 22, it asks us to calculate the distance for the first 10 seconds. And so I would find the area of this triangle here. The area of the triangle is 1/2 base times height. That's 1/2 10 seconds times 10 meters per second. That comes out to be 50 meters. All right, so I hope that was a good review of Unit 1 and the exam, Unit 2 and the exam for Unit 2. If you have any questions, make sure you ask me in class or come to Remedial.